Hey, it's Mr. K doing a video for AP Physics 1, and we are looking at some conservation of energy problems, some work energy theorem. These are just some practice problems to help you through it. We have mastering physics, and one of the problems in mastering physics, I think the first one, is where you have a guy, and he's pushing him on a piano, and the piano is sliding down an inclined plane, and my guy's probably going to fall backwards, but whatever. And the key here is that the velocity of everything is constant. Alright, so that is some unknown velocity. Don't really know what it is, but it is constant. And what we know if it's constant is that the change in kinetic energy of the object is nothing. So let's take a look back at conservation of energy. We're looking at mechanical energy, so we're talking about spring potential energy. We're talking about mechanical energy. Well, kinetic energy. We're talking about potential energy due to gravity. Anything that is really caused by forces is going to be mechanical energy in this case. So looking at the problem, we have this guy who is pushing up on this box, and this box is sliding down the incline at a constant rate, and it goes 2 meters. And so 2 meters down the incline here, we're not talking about a change in height of the 2 meters, we're talking about this 2 meters of the incline, and if I make it 30 degrees, I can find a change in height if I want to. And just to do that, we're going to take 30 sine 30, multiply that by the 2, that's going to be 1. Yep. And so we do get a change in height of 1 meter. Now that could be useful for us, that could not. Let's see what the question is saying here. The question says, man, piano, angle, determine the force exerted by the man. So that first question is just free body diagrams, determine the force exerted by the man on the piano. And so if we look at the free body diagram of the piano, we know that the piano has a force of gravity downwards on it, which is our mg. This is what we're used to. We also know that the normal force of the piano on the table or on the incline should be going up this way. That would be perpendicular to the incline. So normal force would be right there. Also, we know that we have a bit of a force of push, an applied force from the guy, and that should be up in this direction. I'll call that an applied force, Fa, and that is going to cancel out our force of gravity that pushes us down the inclined plane due to gravity. So remember that this whole system wants to move down the inclined plane in this direction. And so if we have it going down in that direction, we want to break our forces into the components that are in that direction and totally perpendicular to it. And so here our angle would be our 30 degrees. Our gravity, our force gravity, would have a component in this direction. And we would find that by using not mg, but mg sine theta, because it's the opposite side to my angle there. And this side's going to be mg cosine theta. Don't think we're going to use that too much, but we'll just write it down because, you know, just to remind us how everything works. And alright, so the question was, how much force is exerted by the man? And if I look at my free body diagram, if I tilt it, I know that the force applied by the man here should be equal to the amount of force that is the mg sine theta. So for our x direction, the sum of all forces is equal to, in the x direction, mg sine theta minus the force of the guy that applied, and that should equal to 0 because I know I'm not accelerating in any direction. And by math, that says that the force applied is equal to our mg sine theta. So we could have done that really fast, but I just wanted to write out all of the steps. And so here, if I know my m is going to be 200, my g is going to be 9.8 or 10. We use 10 right now. Mastering physics use 9.8. And then multiplied by the sine of 30. Sine of 30 is just a half, and so that should equal 1,000. So that would be the answer for the first part. Of course, your numbers will be different from mine. The next part says, determine the work done on the piano by the man. So work, we're going to do part B here, work is equal to a force parallel to some distance that we're going to go, and the guy is pushing up in this direction, And so that force is going to be completely opposite of the displacement down the incline. Um, Work is also equal to a change in kinetic energy, or an attempted change in kinetic energy, if we're looking at net work. Here, the guy is trying to slow the piano down. Without the guy, the piano would speed up. And so for us, this work done by the guy is probably going to be negative. He's pushing against this direction of motion. And so the force, again, for me, or right now I use easy numbers, is 1,000. And that applied distance is going to be 2 meters. And so I'll put a negative there for the amount of amount of force applied, and this will be negative 2,000. Negative 2,000, the unit would be joules. Joules. So this guy is trying to take energy out of the box or the piano as it slides down the incline, whereas gravity is trying to give the energy to the piano, make it go faster. But the guy's preventing that. And let's see, part C says, determine the work done on the piano by the force of gravity. Well, I know that the piano is trying to make this thing go faster with this force here. This force is 1,000, and so the work done, this is by the guy, or man, this will be from the piano. And so for the piano, we're talking about another force times distance, and they're in the same direction of motion. And so that's just 1,000, because that mg sine theta, and that's going to be multiplied by the distance of 2 meters. And that's going to be a positive 2,000 joules of work. So that should make sense. That should make a little bit of sense because the guy is taking energy out of the piano. The gravity, the force gravity is putting energy into the piano. There is no change in overall energy, so we have no speeding up and no slowing down. That's what we want. All right. Let's just prove a point though, that if we were to actually write down the force mg sine of theta multiplied by that distance d, as we kind of did in the first place where we found out the height change there, sine of theta times d, this distance here, would just be h. And so really the work done by the force gravity on this piano is just mgh. You know, just to go back and prove a point that this is the potential energy due to gravity. Here we're looking at it in terms of work. Same thing really. It just depends on how you're talking about your problem, how you're setting up your system. So if we wanted to say that the system is the piano and the earth, we would be using this term, potential energy due to gravity. Because right now we're just talking about the piano itself and the forces that are just concerned with the piano, then we'll call it work. The next part says determine the net work done on the piano, and we've already figured that one out. The net work done on the piano is equal to the sum of all the work done on the piano. And so we're going to say that this is the work done by the man and the work done by the piano. And as you probably just figured out, there is no net work done on the piano by the guy and the force gravity itself. So in total, no total net work done, no change in kinetic energy, no change in velocity, constant velocity. It's very important. And then we can resolve the forces into their individual parts and find out how much work each one did. That's the problem. Gonna do one more for this one. We're just practicing problems here. There's a bunch of problems that we can practice, but I think this one's a pretty good one because we have done problems like these before, but just not in terms of energy. So let's go ahead and talk about an Atwood's machine. And remember that an Atwood's machine is just a pulley. And for right now, we're going to use a massless as well as frictionless pulley. We keep on saying this, but until we get to rotational motion in the spring, we really want to keep these as massless and frictionless, because if it does have mass, if it does have friction, then the energy is just not with the two boxes, but also now with the pulley itself. You got to have energy to move it and everything. So let's not give it mass just yet. So we have mass 1 up here, we have mass 2 down here. Let's say that mass 1 falls down a certain distance. Let's just call it like 10 meters. And then mass 1, we're going to make it, let's make it 10 kilograms. And then let's make mass 2 like half that, so 5 kilograms. And the question is, what is the final velocity when mass 1 falls all the way down? Same thing, what is the final velocity of mass 2 when mass 2 rises up because mass 1 has fallen down? So usually what we would do is we would look at the forces in the problem, and we would say, all right, here is mass 2. We know that it has a force of gravity downwards on it. We know that there's a force of tension upwards on it. That's probably a little bit bigger than the force of gravity on it. So force of gravity on it is going to be 5 times 10, or 5 times 9.8, and that's going to be 50 knot joules, newtons. The force tension up on it is, I don't know what it is, but it's bigger than 50. We're going to go over here to mass 1, and it has a force of gravity down on it, which is going to be double the size of the 50. It's going to be 100 newtons downwards. But what we do know is that we have a force upwards on it. That's going to be that same force of tension, but it's not going to be as big as the 100 because this thing does need to accelerate downwards. So forces and the dynamics section, the dynamics unit still comes into play. Don't forget about that. We're going to call this direction positive, and if you want to do that, you can solve this totally with dynamics, but I want to solve it with energy. And so to solve it with energy, we don't really care about directions, let's say. We care about positions. Like, where did something start, what happened to it as time went on, as distance was traveled, and then what's going on with it later. So let's identify the types of energy in the first place, and the identification of energy in the first place is going to be potential energy. Let me use a different color. That M1 has a potential energy due to gravity, UG, up here. And that's it in the beginning. M1 falls down. As M1 falls down, M2 rises up. M1 will get faster as it falls. M2 gets faster as it rises. But then M2 ends up with some potential energy in the end. And so the statement of conservation of energy would say that the energy in the beginning should be equal to the energy in the end for our system. The system being all of this and plus the Earth. We're gonna include the Earth here because we want to talk about potential energy. We don't just want to talk about work. If you wanted to consider just one object, M1, let's say, we can use work energy theorem and saying, all right, what's going on with M1 in the beginning? Well, it has no energy, pretty much, but we're going to give it energy because the force of gravity is going to pull on it, and so the energy of M1 is going to be equal to the change in that potential energy due to gravity, the work done by gravity on it. So it's going to gain energy, it's going to get faster, that potential is going to be turned into kinetic. Same thing for M2. Work energy theorem would say, hey, M2 right now in the beginning, it's sitting still, nothing's happening with it, but we're going to push on it, gravity is going to push on it, or actually, tension is going to push on it upwards, gravity is going to try to pull on it downwards to take the energy out. But because tension's bigger than force gravity on M2, it's going to gain kinetic energy on the way up. Okay, but also it's going to gain potential energy as well. We're going to use conservation of energy though. It's going to be a lot simpler. So conservation of energy would say, who's got the energy in the beginning? That's M1. M1G H, or delta H, is going to be the energy that we have in the beginning. After things have moved, after things have transitioned down and up, we're going to say that M1 no longer has any potential energy. It's going to be Mg0. So I'm not even going to write it. But we do know that M2 is going to have some rise in potential energy. It moves upwards. And then we're also going to add in some 1/2 M1V squared because, hey, it's moving now. And then we're going to also add in some 1/2 M2V squared because it's also moving. It's moving at the same speed. So looking at this, if we want to figure out the final velocity, then we're just going to have to move everything else over. So let's take the M1G delta H minus M2G delta H. Let's move that over by subtraction. And then that's equal to 1/2 M1V squared plus 1/2 M2V squared. Let's make this look a little bit nicer. Let's take that 1/2 and let's move it out. So 1/2, and we're also going to move that V squared out, and so that would leave us with M1 plus M2 quantity V squared. Yeah. And let's see if we can't do a little bit more math here. Let's multiply everything by 2. So let's also factor out stuff over here. So we've got M1 minus M2 G and H, because those were the same. We can factor those out. Multiply by 2, and this is equal to M1 plus M2 quantity times V squared. We're pretty much there. We didn't have to do this many algebraic steps to show, but I'm doing it because some people definitely need the assistance with algebra. So dividing by M1 plus M2, 2 M1 minus M2 G delta H divided by M1 plus M2, and that's equal to V squared, so we're just going to square root all that. So that would be the algebraic derivation of the velocity of these objects at the very end. You could easily do this with dynamics, using forces to find acceleration, and then using some kinematics, but I think you're going to get to the exact same result here as you would if you did forces and kinematics. Okay, plug in numbers, we'll finish this off. 2, the difference between the masses is going to be 5 kilograms. G is just 10. Some of you might wonder why we won't use negative 10 there. It's because we're using just straight up positive value of G. The delta H, if you wanted to use negative G, the delta H would be negative 2. But let's not worry about it. So 2 times 5 difference times 10 times another 10, the change in height, divided by M1 plus M2, it's going to be 15. And then we're going to square root. What does that give me? That gives me 5 times 5, that's 10 times 10 times 10, so 1,000 divided by 15, so 2 times 5 times 10 times 10 over 15, square rooted, not logged, but square rooted, and I get about 8.165 meters per second. And this is for both objects. M1 is moving down at 8.165, M2 is moving up at 8.165 meters per second. And that would solve the problem for us here. So, more practice, a lot of practice. We're going to practice a lot. I'll stop the video here though.